When we estimate risk measures like VaR or expected shortfall from historical data, the number we get is not exact. It's only an estimate. If you take a different sample of returns, you will get a slightly different VaR, sometimes higher, sometimes lower. So the big question is, how reliable is our estimate? That reliability is measured using something called the standard error. Think of standard error as the precision of your risk number. If the standard error is small, your VaR is stable and trustworthy. If it's large, your estimate is noisy and uncertain. Now remember, VaR is simply a quantile of the loss distribution. A 95% VaR just means the 95th percentile. In other words, 95% of losses are smaller than this number. So when we estimate VaR from data, we are really estimating a sample quantile. And like any statistic calculated from a sample, this quantile has variability. It moves around from sample to sample. Statistics tells us that the variance of this quantile estimator depends on three things: the confidence level P, the sample size N, and the density of the distribution at the VaR point. Without worrying too much about the formula, the key message is simple. The variance gets smaller when the sample size increases, and it gets larger when we go deeper into the tail. The standard error is just the square root of this variance. And practically, it tells us the typical estimation mistake we might make. For example, suppose your 95% VaR estimate is 1.65 and the standard error is 0.10. That means if you repeated the experiment many times, the VaR would usually fluctuate by about plus or minus 0.10. So the number 1.65 is not exact. It's only approximate. Once we have the standard error, we can also build a confidence interval. Just like in basic statistics, we use estimate plus or minus 1.96 times the standard error. So if VaR is 1.65 and the standard error is 0.10, the confidence interval becomes 1.65 plus or minus 0.20, which gives a range from 1.45 to 1.85. This means the true VaR is likely to lie somewhere inside this interval, not exactly at 1.65. This helps us understand how uncertain our risk estimate really is. In practice, there are different ways to calculate the standard error. If we assume a parametric distribution like the normal distribution, we can directly use the analytical formula. This method is quick but depends heavily on the distribution assumption. A more practical and widely used method is bootstrap. Here, we repeatedly resample the historical returns with replacement, compute VaR again and again, maybe 1,000 times, and then take the standard deviation of all those VaR estimates. That standard deviation becomes the standard error. It's very intuitive, doesn't require distribution assumptions, and works for both VaR and expected shortfall. There's also asymptotic theory, which tells us that for large samples, the standard error roughly decreases at the rate of 1 over square root of n. There are a few very important relationships you should always remember. First, if the sample size increases, the standard error decreases because more data gives a more stable estimate. Second, if you move to higher confidence levels like 99% VaR, the standard error increases because tail events are rare and harder to estimate accurately. Third, if the density around the VaR point is low, meaning fewer observations in that region, the estimate becomes more volatile. And finally, expected shortfall usually has a larger standard error than VaR because it uses only extreme tail losses and averages them, which makes it even noisier. So when evaluating estimators, smaller standard error means a better, more reliable risk measure. So the big takeaway is this: VaR or ES tells you how big the loss can be, but the standard error tells you how sure you are about that number. And in risk management, knowing the uncertainty of your estimate is just as important as the estimate itself.